we're going to go through a few more examples, a couple more examples of partial fraction decomposition on this video. So just a reminder of our partial fraction decomposition process is projected on the screen right now. So what we're going to do is we're going to start by double checking that our rational function is in proper form. Use long division if not to put it into proper form. Then we will factor our denominator completely. Once the denominator is factored into linear and irreducible quadratic factors, we will use our partial fraction decomposition algebraic theory here, and we will break down our rational function into partial fractions. Then we're going to set that rational expression equal to its partial fraction decomposition, clear out the denominator by multiplying both sides by q of x, and then use some algebra to determine the constants for each of the partial fractions. Then we replace those constants in the partial fraction decomposition and integrate by type. All right, let's take a look at some examples. Starting with this one, we notice first off that we are in proper form because the degree of the top is 2 and the degree of the denominator is 3. So we're definitely in proper form. We don't need to go through any long division on this problem to put it into proper form. Next thing we're going to do is we're going to factor the denominator completely. So this denominator will become, whoa, I'm going to zoom in a little. I'm pretty zoomed out there. The denominator, I'm going to rewrite the top. 4x squared minus x plus 10. We're not doing anything on the top. In the bottom, I notice I've got a common factor of x, so let's pull that out first and see if there's anything more to do. And there is not, because x squared plus 4 isn't irreducible. That does not factor any further. So that's irreducible quadratic. It is not repeated. It is only to the first power. And this is a linear factor. It is also not repeated because it is only to the first power. So we will use our algebraic theory to break that down. We're going to end up with just two partial fractions, one of them coming from the linear factor. So it will be of the form a constant, we'll call it a, over x. And then we have that irreducible quadratic, x squared plus 4. Now when we break that down, its numerator will be a linear expression, bx plus c. And I'm just going, right, I started with a, so then my next constant I need to find will be, we'll just call it b, and then c. So I just go down in the alphabet. Of course, you could use any constants you want when you're setting those up. Now, what we're going to do is figure out what those constants are so that we can actually plug them back in and then integrate. So this is where we come off to the side and we do some side work, some algebra. Now, again, I'm going to do it one way, and I don't think on this video I will show both ways, but you can use either the equating of coefficients and setting up a system of equations, or you can use the strategic choosing of x values. So that's kind of up to you, but either way, you got to find those constants. So let's take 4x squared minus x plus 10 over x times x squared plus 4, and that was equal to my partial fraction breakdown, a over x plus bx plus c over x squared plus 4. We're going to clear the denominators by multiplying by the q of x, the factored denominator on the left side here, and I'm going to multiply every single term, both sides of the equation to keep my equality. That will clear out the fractions, and I will end up with 4x squared minus x plus 10. Over here, the x's will cancel, so I'll get a times x squared plus 4. Then I have bx plus c, that whole numerator, times now the x squared plus 4's cancel on that term. And we end up with bx plus c times just x. Now I'm going to go ahead and expand both sides. Actually, well, there's nothing to expand on the left side, but I'm going to expand the right side so that I can equate coefficients. So ax squared plus 4a plus bx squared plus cx. Now I look and I collect my like terms. I've got two x squared terms. So I collect each of those, and the coefficient will be a plus b times x squared. I have just a single x term, so I will write it in descending order, so that'll be just c times x. I'll write it with the parentheses, even though there was nothing else, plus, and then the constant term there is the 4a. So the constant term is 4a. And I guess we could put that in parentheses if we wanted to. Those parentheses aren't really necessary. I guess I'll get rid of them. If you had more than one term, of course, we would have the parentheses. on them. Then we've got 4x squared minus x plus 10. Now what we can do is we can equate coefficients. So we look, right, we've got equality. And so what we do here is we say, okay, well, on the x squared term, on the left side of the equation, the coefficient is 4. And the right side of the equation, the coefficient is a plus b. So 4 must be equal to a plus b. And then we keep going. So we've got a negative, this is a negative 1. Negative 1 must be equal to, well, on this case, c is simply the only term in the coefficient on the right side of the equation. So that right there, we know that c has to be equal to negative 1. And then we also know that the constant, highlight the constant is 10, and the constant on the left side and the constant on the right side is 4a. So 10 must be equal to 4a. And this system worked out really nicely because we can clearly see we already have C. A is really easy to solve for. A is going to be 10 over 4, which is 5 halves. So we also know A. And then we can quickly find B by plugging in here. 4 equals, we'll plug in our A, which was 5 halves, equals, oops, plus B, not equals. And we'll solve for B. B is going to be 4 minus 5 halves, so that is 3 halves. So B, that was B. B is 3 halves. And we have everything we need to plug back in. I'm not going to go through the other way, the strategic picking of x values. You know what I will talk about real quick on this one? Like, I'm not going to go through it, but the strategic picking of x values, if we bring our eye to this line right here, the strategic picking of x values, we could easily pick x equals 0, and then we could use that to solve for a. That would give us a. But what would we pick here to zero this factor out? And that is actually, you could actually use a complex number. You could let x be 2i. And this theory, the strategic picking of x values, works across the complex field too. That's beyond the scope of this course. Like, I won't go through any of those examples, but I have had students that have played around with that a little bit in the past, and that's kind of a fun little side tangent on working with complex numbers as well. But either way, this nice little expansion and setting the coefficients equal to each other gave us all of our constants. So we have all our constants. So let's plug them back in and get into the integration of this rather than spending any more time on finding the constants because we've got them. So a was 5 halves, so 5 halves over x. I know I'm zoomed way out right now, but let me write these constants down and then we'll zoom in on the integral. Then we had 3 halves x, and my c was a negative 1, and that was all over x squared plus 4. And now we need to integrate that. So let's zoom in and get into our integration here. Oh, I wrote c, but c was, what was c again? I think it was just minus 1. Yes. So c is minus 1. All right. Here we could just leave it. We've got those fractions in the top, but fractions are not the enemy. Fractions, while carrying them along, might be a little bit of a pain. They're not too bad. We could leave that 5 halves and that 3 halves and just work our way through this integral in that way. But just as a algebra technique here, arithmetic really, we're going to factor a 3 halves or a 1. I was going to say 3 halves, but actually I just want to do a 1 half out. I'm going to factor a 1 half out. And then that way I won't have to deal with fractions. So when I do that, when I pull a 1 half from each of these numerators, this of course is just going to become 5 over x. This will become 3x minus 2 because I'm taking a 1 half, I'm dividing each of these by a 1 half. So when I factor it out, I have to remember I'm doing it to both of the terms. So I'm pulling out that 1 half from both of those terms. Technically, I'm dividing negative 1 by 2. So getting that 3x minus 2 over x squared plus 4. So I just wanted to explain that step real quick when I do that simplification. I do like to clean up my fractions and pull my fractions out, but you could also just leave your fractions in and integrate, but just make sure you track the fractions and continue carrying them throughout. I, on the other hand, am going to pull 1 half out, and then I can just integrate each of these fractions by its form. So obviously this first fraction is going to just be 1 half when I integrate 5x. That is going to become 5 times the natural log of the absolute value of 5. Now, I still have this integral to deal with, and this sort of bumps us back a few sections, thinking about how am I going to integrate that? Because in its current form, I can't do a substitution, because if I let u be my whole denominator, my du would only be 2x, and I have two terms in the top. So this goes back into basic integration strategies. When we do have two terms in the top like that, one of our strategies is to split that in further into two fractions, right? We've already split up into partial fractions, but we can continue to split this integral into two fractions. This is going to be a minus 2 over x squared plus 4 dx. In fact, I'm going to pull that 2 and that 3 all the way out. Do a couple things at once. Okay, now each one of those can be handled in a slightly different way, because on the first integral here, now I can do a substitution. I could say u equals x squared plus 4, and du is 2x dx, so that x dx is 1/2 du. And I'm going to finish this integral and we'll come back and look at the other one. So that's going to become plus 3 times the integral of, we've got that 1/2. So we end up with 1, the x dx becomes 1/2 du. So I get 1 over u du, but we had that 1/2. So I'm going to divide by 2 right there. I was, technically I had a 1/2 du right there, but I'm moving the 1/2 out in front. And I think we should be pretty comfortable with substitution, be able to do that pretty quickly. So this becomes 3/2. This, of course, this integral right here is simply the natural log of the absolute value of u. And so this becomes 3/2 natural log of the absolute value of x squared plus 4. I actually don't need the absolute value on that, because that becomes, since we're plugging in x squared plus 4, that is always positive, so I could actually drop the absolute value and just write it as 3/2 natural log of x squared plus 4. Now that was just one piece of my integral. I need to carry the rest of all of this down. I had 5 natural log of the absolute value of x right here. Okay, I'm going to just, we're going to bring that all the way down here. So we have 1/2 and 5 natural log of the absolute value of x. I'm going to have my first two fractions have been broken down and integrated. Now let's take a look at this one. This, notice, is an inverse arctan. Remember when we integrate 1 over x squared plus a squared dx, little recall here, this is one of the integrals that we should know. We should have this memorized. This is going to become 1 over a inverse tangent of x over a plus c. We should have that guy memorized and recognize it. Our a in this case, of course, is 2. So this is x squared plus 2. We recognize this guy and we say, that integral is just going to become, it was a minus 2. It's going to become 1/2, 1 over a, inverse tangent of x over 2. And then we can carry that all the way down as well. And we end up with minus inverse tangent of x over 2, because the 2's would cancel, and a plus c. Now, when I'm looking at that, that is a perfectly acceptable answer. We could just leave it as is. I do notice, again, right, it's hard when I see those logs. I see them and I think, we could simplify that a little bit further, because that could come in as a 5th power. That could come in as a 3/2 power. And the plus right here, we could bring that into a product once we've brought the powers in. And so if we really wanted to get algebraically creative here, it's not really creative, just applying our algebra rules here, we could write this as the natural log of the absolute value of x to the 5th times x squared plus 4 to the 3/2. Bringing our logs together using just applying our rules of logs on powers and products. And then we've got our inverse tangent, or arctan if you prefer that notation, x over 2 plus c. So just as a side note, we could use some algebra to bring those terms together. Okay, so again, right, we're getting into some nice integration problems where we're applying our strategy of partial fraction decomposition, and then when we get into the integration, depending on each of the fractions, we're using slightly different integration strategies on each of the fractions. All right, let's take a look at one more example. This one is already in its most factored form. This guy here, x minus 1, is of course a linear factor. X squared plus 4x plus 5 is an irreducible quadratic. So this is quadratic, it is irreducible, it cannot be factored further, and this is a linear factor. So we've got a linear factor, an irreducible quadratic factor. Neither one can be simplified, neither one is repeated. So I should mention, we should double check that this is in proper form. And the power in the numerator is an x squared. When we're given our factored form, we might have to do a little more work just to double check that it's in proper form. But notice here that the highest power in the denominator, because we're taking an x minus 1 times an x squared plus 4x, the highest power down here, the degree is going to come off of x cubed. So the degree in the bottom is an x cubed, so we are in proper form. But we should always think about that. I almost glossed over that for a second and jumped right into the breakdown. But now let's get to the breakdown. So we've got a over x minus 1. We get one partial fraction from the linear factor, and then we're going to get one partial fraction from the irreducible quadratic, x squared plus 4x plus 5. So we've got those two partial fractions. We're going to come off to the side and work our side work to find those coefficients, those constants from the equating coefficients. And we're going to take x squared over x minus 1 times x squared plus 4x plus 5. We're going to set that equal to a over x minus 1 plus bx plus c over x squared plus 4x plus 5. We're going to multiply both sides by that denominator. And I'm going to speed up the video through here. Okay, so I did a bunch of that algebra just to speed up this video a little bit. We've been doing, this is now our fifth example. So you've seen me equate the coefficients. I equated the coefficients. I did some elimination strategy. You could have also used substitution here. I did elimination strategy to find my coefficients. I found a, b, and c, and I plugged them back into my integral. And then I just did that little algebra technique to play with the fractions or make the fractions a little nicer to work with by factoring a 1/10 out. Since 10 was the lowest common denominator of all those fractions, I factored a 1/10 out, and that left me with where I'm at right now. So now let's get into each of these and let's integrate each one of these by form. Now, this first one we can integrate. I'm going to go ahead and also look at each of these integrals individually. So we have the 1/10 and we've got 1 over x. Now on that one I can do that's a quick u sub because u equals x minus 1 and du is just dx. So this becomes the integral of 1 over u du when I make the substitution, which is the natural log of the absolute value of u. So on that first integral, we're going to end up with the natural log of the absolute value of x minus 1. Now, the other part, this second fraction, I need to work with that, and that guy is definitely some of our techniques. We have to apply some of our algebra techniques, some of our integration strategies. I notice on this one that I have a irreducible quadratic, but I could complete the square to get it in the form of a u squared plus a squared. So I'm kind of thinking about that. I'm thinking, okay, I got to complete the square here. So if I want to complete the square, right, that's my thought process here, my little thought bubble over here. If I want to complete the square, this is going to become, let's go back to black. We've got x squared plus 4x on the bottom. I'll put the 5 out here. I'm going to go ahead and add 4 to make that into a perfect square, x plus 2 squared. But if I add 4, I also need to subtract 4. So my denominator there, I'm going to go ahead and rewrite my integral, becomes x plus 2 quantity squared plus 1. Now that's what I'm going to work with. That's what I'm going to integrate. So I'm looking at that and I'm thinking, whew, man, that's still not integrable because I have the 9x plus 5. But at this point, I do want to write that as u squared plus a. So at this point, let's make, and this is a separate u sub from what we did here. We're focused on just this integral. But let's do a similar, not a similar, let's do another substitution. So let's let u be x plus 2 so that that will eliminate that piece or be able to plug in right there. And then my du is just dx, so I'll be able to make that substitution. But notice in the top, I've got a 9x plus 5, so there's a kind of a leftover x there that I need to deal with, but x is equal to u minus 2. So I'm going to make those substitutions, and so this is going to become the integral of 9 times u minus 2 plus 5. In the denominator now, I'm getting closer to something I will be able to work with nicely. I've got u squared plus 1 there, and du is actually just equal to dx, so we'll make the substitution there. Okay, let's keep going. I'm going to keep integrating, or actually, I'm not going to integrate yet, but I'm going to keep simplifying. In the top, I get 9u minus 18 plus 5, so that becomes 9u minus 13. And that is over u squared plus 1 du. Now, again, I can't integrate this, but I'm seeing that u squared plus 1 in the bottom. And if it was just a constant in the top, I know that that's going to be an arctan or an inverse tan. It's not just a constant in the top, but it is 2 terms in the top. So now I'm going to use the strategy of splitting this fraction up. So notice we're using all of these like tools and techniques, these algebra tools, the completing of the square, and now splitting up a fraction. So now let's split up the fractions here. I will carry the other terms down on the integral. I want to finish dealing with just this piece first. So this is going to become the integral of 9u over u squared plus 1 du plus, actually minus, the integral of 13 over u squared plus 1 du. Now that part is definitely an inverse tangent, so that's minus 13. Inverse tangent, the a is actually just 1 there, so inverse tangent of u. I'll throw my integration constant that we're going to have here in the end. This piece here is going to involve another substitution, so let's let it be w. W equals u squared plus 1, so my dw is 2u du. Keep track of all my variables here. And then my 1/2 dw equals u du, and I can make those substitutions. So this becomes 9 on the outside. My u du is being replaced with 1/2 du, so I'm also going to have a 1/2. I'm going to pull that out. I'm going to get 1 over w dw. So remember when I substituted for u, this u du, I'm going kind of fast here, but that u du was a 1/2 dw, and then that 1/2 I just pulled out in the front since it was a constant and brought the 9 out as well. Okay, so we'll keep going there. That's now going to be just 9/2 natural log of the absolute value of w. Carry down our minus 13 inverse tangent of u. And now let's work our way backwards through the substitutions. So we've got 9/2 natural log. Our w was u squared plus 1, and our u was x plus 2. Get it up on the board. There it is, right there. So working our way backwards. So our u was x squared plus 2, so I'm going to write that in, x squared plus 2 squared plus 1. We need that here as well, so minus 13 inverse tangent of x plus 2. I think I wrote x squared plus 2, but it was just x. U was just x plus 2. I'm trying to go too fast here. Plus c. All right, so carrying everything down, we're still missing that original term, and I just didn't want to have to rewrite it 500 times there, or 14 times, however many times it would have been. So we have 1/10 times all of this, natural log of the absolute value of x minus 1 times, let's see. Okay, let's see if I can get this all on the board here. So our final answer on this one, and it is kind of a crazy answer, right? We end up with 1/10 natural log of x minus 1 plus 9/2 natural log of x plus 2 quantity squared plus 1 minus 13 inverse tangent of x plus 2, all plus an integration constant. Whew! Woo-wee! We had a lot going on there. All right. So there is, let's see if I can, I don't even know if I can get all this on the board, but let's try. Let's try to get that all on the board there, and we can see what we got.